Okay, welcome. This is Professor Elliott, and we're going to look at a combination bridge rectifier, Zener diode, and LED circuit today. So we have our AC sine wave. So let's say we have 120 volts on our primary. We have 18 volts on our secondary. You can work out the turns ratio if you want. Doesn't make any difference to us. Note the polarity of the diodes here. So that means then this output, so this diode right here is going to conduct when that point is negative and that point is positive. Then the current then, right, is going to go like this, right, down like this, right, and then down, and then down, and then down. These two are common together, right, and then all the way back up like this, and then down like that. So the output voltage is going to be negative. Okay, good. So what is our output? Okay, so we have 18 volts secondary RMS equals 18 divided by 0.707 equals 25.46. Sorry about that. 46 volts peak, right, minus 2 diode drops. So this is the peak secondary voltage, right, minus 1.4 equals 24.06 volts peak. And that's the peak voltage coming out of the rectifier. So that would be right there. Fair enough? Okay, next. Okay, so assuming we have a nominal forward voltage drop on the LED of 2.5 volts, which was given right here. So that would mean then that, and these be all the, right? So the peak VO equals 24.06 volts. Okay, and so the output will look like, okay, no, these are all actually, because the output's negative, actually negative. So the output's going to look like, and this is full wave. So that's going to be 0, and this is going to be our minus 24, or 24 volts like that. Okay, so the LED, look at the orientation of the cathode. LED will be forward biased. Right? So let's convert the output into DC. So that would be 24.06 volts times 0.636 equals 15. Of course, this is minus 0.3 volts average, right? So you're just taking the average value of this. Okay, so we could say then that V, these are all in average voltages, VR1, so that would be approximately 15.3 minus 2.5 minus 2.5 equals 12.8 volts average, and then the current, then just divide that by the 560, would be around 22, and I know this is negative, 22.8 milliamps. Okay, so that would be the current flowing through resistor R1. So all we did, we subtracted the forward drop, the 2.5 on the LED away from VO. That gives us our 24 volts times the 636, gives us the average output, right? And minus the 2.5, and that gives us 12.8 divided by the 560 gives us about 12.8, almost 23 milliamps output. So the only thing left to do is to look at the voltage across the Zener. Notice that if this output is minus, that means that this point is positive with respect to the output, so the Zener is reverse bias, so it's acting like a Zener. Okay, so I'm just going to I think resketch that a little bit partially on the next page, like that. That was 330. Okay, this is going to be R2, and that was VZ was 8.1. And this is VO. So again, VO average, VO average, okay, equals so this is where I'm getting it from, so that's going to be this one right here, right? Oops. Sorry, a little bit too much. Minus 15.3 volts. Just go back. Yes. Okay, so therefore then voltage V, so V2 must equal VO minus VZ. We know this is all going to be negative, so we're just going to drop it. Add it in later. Okay, 15.3 minus, that equals minus 7.2 volts. Average. And IZ equals 21.8 milliamps. K, which is simply V2 divided by R2. Okay, a couple other things. So I'll go back. Yeah, is that I'm going to use a highlighter. Okay, so this point here, this is the, maybe I'll use a, this is the common, which is often used as the ground, but not in this case. Excuse me. This is the common, and this is the common. So these three are all connected together. So that means then, if you wanted to display the waveform, the secondary waveform on the 18 volts, you'd have to connect your channel 1, like the lead there, and the ground clip there, because there can only be one ground in the circuit, remember? So that would display your 18 volts, your secondary waveform. Do not connect these three common points to the ground, because otherwise you'll have a ground on the transformer and on the diodes, and you're going to cause some problems. So if you're using the scope, make sure these three places are connected to this common, but they're not actually connected to ground. Otherwise, you're going to run into difficulty. Okay, and again, that was minus 15.3. Okay, so I think that's about it. If we were to change the orientation of the diodes around, we would get a positive output, but such as it is, this is going to be negative. So, okay, I guess that's it. We'll catch you later. Cheers.